Hey everyone, we're starting a new chapter today, and this is chapter 8, which gives us more applications of integrals, and this will be some geometric applications and some physical applications. So the first of the applications we want to look at is arc length. And so the picture goes like this. Let's say that we've got some graph, right, some curve going from A to B. The question is, what's the length of that? Right? If I asked you, okay, I'd like you to tell me how long this portion of the curve is, what would you do? Or what would be a way to figure the answer out? Right? How long is that? Well, one way to think about this would be to say, all right, what if we took a piece of string and we sort of glued or taped, somehow made that piece of string match the shape of that graph, trace the shape of that graph all the way, right? And once you've done that, then you could take it, pull it tight, and then measure it with a ruler. And that's the key. The way we measure distance is with straight lines. Here we've got a curve, and so we're going to somehow need to adapt our approach to measuring, which is by looking at straight lines or using straight line distance, right? And adapt that to curves. And the idea is our usual thing. When we want to find a length or approximate, or I shouldn't say approximate, when we want to compute a new geometric quantity, what we do is we first approximate it, and then we get better and better approximations. So what we're going to do here is we're going to chop up the interval from A to B into a bunch of pieces. That's our partition process, right? So step one, partition the interval from A to B, and so that will be A equals x0 less than x1 less than dot 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 less than xn, which equals b, right? So chop the interval up into n pieces. So here I've got an x1, x2, x3, x4. We call A equal to x0 and we call B x5. I did 5 pieces. It doesn't need to be, I mean, it could be n, whatever n is. In this case, I did 5. Right, so chop them up into equal pieces. And now what I want to do is go up and mark the graph. So go straight up from each of those marked points, or each of those points, and mark the graph. And then I want to join adjacent points by straight line segments. Like that. So if I added up the lengths of each of those straight line segments, it would not be exact. There's definitely some error, but it would be an approximation. And then if I said, oh, okay, let's choose smaller, let's chop this up into more pieces so that we get smaller subintervals, then the pieces that we join with will be, will have less error, we'll get a better approximation. So partition like this. So now, next step, join adjacent points. So let's see, who is this point right there? x1, f of x1, that point right there, x2, comma, f of x2, etc. So let's say it like this, join the adjacent points, so that'll be an x sub I minus 1, comma, f sub x I minus 1. And x sub I, comma, f sub f x sub I, by a line segment, let's say by a segment, its length is, okay, so now we're just going to use the distance formula to compute the distance between 2 points. So its length is going to be square root. So let's see, you subtract the x coordinates. So that will be an x sub I minus x sub I minus 1 squared. All right, so you subtract x coordinates, square the result. Subtract y coordinates. Square the result. Add those together, take the square root, that's the length. Okay, now this is a mess. What I'd like to do is simplify this. So let's see if we can make some sense of what we get from the distance formula. So this, I'm going to do it over here, but this is equal to, so let's see, what do I want to do? All right, I'm going to factor x sub I minus x sub I minus 1 squared out of each piece. So this will be an x sub I minus x sub I minus 1 squared times 1 plus fx sub I minus fx sub I minus 1 over x sub I minus x sub I minus 1, all of that squared. I need one more. Right. Missing one set of parentheses there. Now, okay, so it's not clear why I did this, but hopefully you can just check the arithmetic. By distributing here, you'll get back to this stage right here. Now, what is this right here, x sub I minus x sub I minus 1? We usually call that delta x, right? It's the length of any one of those subintervals. So this right here is a delta x squared, and I can pull that delta x, or it's under a square root, I can pull that right out, and now what we'll have is square root of 1 plus fx sub I minus fx sub I minus 1 over x sub I minus x sub I minus 1, all that squared, and then followed by a delta x, right? So I took the square root of the delta x, took it outside of the square root. Now, inside the parentheses, this should look familiar. This should remind you kind of like of a derivative. And now you need to remember back to Calc 1. There was a theorem that was called the mean value theorem. And it said anytime, so let me draw you the picture here. Right? If you have two points on the graph, this quantity right here represents the slope of the line that joins those two, right? That's called the secant line, right? The line that passes through those. And the mean value theorem says that there is some point in between for which the slope of the graph matches the slope of the secant line, right? That's the mean value theorem. And so there is some point for which the slope of the graph matches that point right there, and I want to call the point where that exists xi star. So this is equal to 1 plus f prime of xi star squared times delta x, right? So here I used the mean value theorem, and this gives us a nice expression for the length of that line segment that we were focusing on. All right, so that's the completion of step 3. That tells us now, or sorry, step 2. So step 3, the length of that curve is approximately equal to the sum of the lengths of those line segments, which can be expressed like this: 1 plus f prime of xi star squared times delta x. Right? So here's a Riemann sum that approximates the length of the curve. So now we all know what to do. As long as that function is continuous, we can say that the length is equal to the limit of the Riemann sum. And in the limit, what you'll get is integral from a to b square root 1 plus f prime of x squared times dx, right? So there is our arc length formula. Okay, so let's try an example. And I should point out now, remember we know that square roots can make integrals difficult. So any of the problems that you're given in your homework, right, when they involve finding the arc length, they're going to have to be rigged one of two ways. Either they're going to be rigged so that you can do some sort of trig substitution that allows you to deal with the the square root, or they'll be rigged so that you'll have a perfect square under the square root, which will then cancel out. So what you'll notice is that the functions that you're given to find the arc length are kind of bizarre looking functions. They're rigged to work out nicely, even though they look weird at first. Okay, so well, let's find the length of, so let's find the length of the graph y equals, and here's one that is kind of weird, natural log of cosine of x over the interval from 0 to pi over 3. All we do is throw it into this formula right here. So I'm going to need the derivative. Let's compute that right away. So y prime is negative sine x over cosine x, which is negative tangent. And so y prime squared is going to be tangent squared, which means that 1 plus y prime squared, that's a 1 plus tangent squared x. That's nice because that's equal to secant squared x. So the length is equal to the integral from 0 to pi over 3 square root of 1 plus the derivative squared, so that's a tangent squared x dx, and then I took it one more step here. 1 plus tangent squared is equal to secant squared. It's under the square root, so what we get is secant x dx. Now we need to remember how to integrate the secant, right? Remember that is natural log absolute value secant x plus tangent x, and we go from 0 to pi over 3. Plug in the limits of integration. This will be natural log of, let's see, secant of pi over 3 is 2, and then tangent of pi over 3 is root 3. Root 3? I don't know why I can't think about that. Yeah, so it's sine of pi over 3 is 1/2 root 3 over 2. Oh no, it's 1 over root 3. Right? So it's sine. No. Sorry. Sine is a root 3 over 2 over 1/2. Yes, root 3. Sorry, it was root 3 to begin with. And when we plug in 0, we will get a 1 plus 0 natural log of that is equal to 0. Right, so there is the answer. Okay, so in the end, finding the arc length, I don't expect you to understand, well, I'd like you to understand the derivation, but you don't need the derivation to compute arc length. All you need is that formula, and then you need to be able to obviously make use of your integration techniques to compute the interval. Okay, so there's arc length, and I want to do one more application here, and that's surface area. So this is going to look kind of familiar. Let's say that you have some graph now, and you look at the region, the portion of that graph that lies over the interval from A to B, and you revolve that graph around the x-axis. This should look familiar from what we studied a while ago when we were studying volumes of solids of revolution. If you revolve that graph, right, you're going to get something like that. And now instead of computing the volume, what we want to do is compute the surface area. So imagine that it's hollow and we just have the skin of this solid. We would like to know the area of that. Well, now this one, I'm not going to make you go through the entire derivation this time. We've seen this a bunch of times, but the idea is going to be very similar to what we did for arc length. What we're going to do is approximate the shape using line segments, which would then give us, let's see if I can fill this out correctly. shapes like that. So if you take a bent line or a diagonal line segment and revolve it around the x-axis, what you get? Well, you get a shape kind of like a volcano on its side. And what is it? It's actually a cone with the top chopped off. It's called a frustrum. Frustrum. I can't remember. Frustrum. I can't remember what it's called. I think it's called a frustrum. Well, now I'm going to look because I'm curious. Oh, they're not even going to say it in here? It's either a frustrum or a frustum. No, I can't remember. Anyways, if you add up the areas, a bunch of these, right, cones with the top chopped off, then what you have, or if you can find the formula or find the area of each of those, you can add those up to get an approximation. So there's the idea behind the derivative, or behind the process of finding the formula. In this case, I'm just going to give you the formula. So if you take a continuous graph over an interval from A to B, revolve it around the x-axis, the surface area is equal to 2 pi. Pi, that should not be surprising, right? Anytime if you're doing something circular, it's not surprising if pi shows up. Integral from A to B, f of x times, and now look at this. This is going to look exactly the same as what we just saw when we did surface area. That also should not be surprising, right? We're approximating the shape of our curve using that same idea, diagonal line segments. Right, so here's the formula for surface area. Let's try an example, and just as before, with arc length, anytime you have square roots, right, square roots can make integrals difficult, and so you'll need either you'll be able to use some technique, or the function will be rigged so that when you compute this 1 plus f prime of x squared, you'll get a perfect square, which will then cancel away. Okay, so let's try an example here. I would like to take the graph y equals square root, and let's take the portion over the interval from 4 to 9. So let's see, the graph of square root goes like that. We want from 4 to 9. So we're looking at that portion. Whoop, I just want the graph. And we're going to revolve it around. So we get sort of a, I don't know what that shape is, but it'll look something like that. The actual shape doesn't matter. All we need to do is throw it into the formula. And so the surface area is equal to 2 pi integral from 4 to 9. Then we take the function, which is square root of x, multiply it by 1 plus the derivative. There's the derivative of square root of x, and then I need to square it. That's equal to 2 pi integral 4 to 9 square root of x, square root of 1 plus, this will be a 1 over 4x dx. And now we just need to integrate this, so let's get a common denominator. So 2 pi integral 4 to 9 square root of x, square root of, so this will be a 4x plus 1 over 4x dx. Combine things now, combine the two square roots. And so what we'll get is the square root of 4x plus 1 over 4 dx. So I just multiplied through, that x will cancel that x right there. And then we've got a 4 under the square root in the denominator, that becomes a 2, cancels with that to give us a pi. Integral 4 to 9 square root 4x plus 1 dx. And now this is an easy integral we can just do substitution. U equals 4x plus 1. Du equals 4 dx. And so we'll get a pi over 4 integral. Let's see, when I put a 4 in here, I get a 17. When I put a 9 in here, I get a 37. And then we have u to the 1/2 du. So that's a pi over 4. And then it'll be a u to the 3/2 over 3/2, going from 17 to 37. So I don't know why this answer is so ugly, but it is. So that will be, let's see, I'm going to flip that over. 2/3 times that will give me a pi over 6 times 37 to the 3/2 minus 17 to the 3/2. So the answer doesn't look pretty, but there it is, right? Not too hard of an integral to compute. Okay, so there you have it. We have arc length and surface area. That's 2 new formulas that you need to know and be able to use. But the main thing will be, once you set it up, being able to use your knowledge of integration techniques to actually compute the integral.